Hi guys, this is Dr. Gonzalez. This is one of several videos that I've made related to variables. This one is specifically oriented to Psych 4371, which is experimental methods and statistics. So I hope that you learned something new from it, even if you've watched my other videos about variables. I'm trying to add a little bit different perspective to it. So remember, if you have any questions, make sure you reach out. And without further ado, let's get started. So on this first slide, I have here a picture of a poster that I saw on Amazon. And it's posting the question, what part of, and then there's this huge image of these things, don't you understand? And I got this idea from a t-shirt that my son has. My son has a shirt that has a bunch of different mathematical terms and formula on it, and it asks, what part of this don't you understand? And it's a great example of how if you don't know what each one of these things represents, then how do you know how to understand the whole shebang? And that's true when it comes to variables. You're going to learn in this particular video that variables are extremely important. We're going to talk about constructs and how constructs play into theories. Then we're going to kind of shift into what an operational definition is and how important those operational definitions are when it comes to doing research, whether it be experimental or non-experimental. We're also going to talk about the role of correlation and positive and negative relationships between variables and how we can use that to establish validity and reliability. Then we're going to transition to measurements, and we're going to talk about validity and reliability of measures. We're also going to talk about the 4 different scales of measurement: nominal, ordinal, interval, and ratio. And you're probably already familiar with those from your previous courses. We're going to talk about the 3 different modalities of measurement and the strengths and weaknesses of each one of those. Then we'll talk about the ceiling and floor effects and how artifacts play a role in our research. So let's start by talking about constructs and operational definitions. So remember, variables are any sort of characteristic or condition that can change, and it has a value. And that value can be different depending on the individual or the situation or whatever it is you're talking about within the research realm. In research, we have to know what the different qualities of those variables are in order to establish criteria for being able to measure them, and also so that we can speak the same language, I guess you should say, with other researchers. So a good variable has to meet a certain set of criteria. So a good variable has to be something that is well defined. I can't leave the definition of a variable up in the air. It has to be very specific. I remember in reading some of the submissions from my last class in the spring this year, their research papers, there were a couple of times when students postulated that they were going to study the relationship between variable X and variable Y. But the definition of variable X was very vague. And that can't happen in research. The definition of a variable has to be very specific. Not only do I have to have a good definition, I have to be able to observe and measure those things that I'm calling variables. So take, for example, height and weight. Height and weight are very good examples of easily defined, easily observed, and easily measured things. Height of a cat, I know what that is. You can conceptualize in your brain when you think of height. You can think of it. You can see what it is in your mind's eye. I can observe it with my eyes, and then I can measure it with a ruler, right? So height and weight are good examples of a variable. But in psychology, and not just psychology, but a lot of other fields as well, we end up working with things that are what we call intangible. They're abstract. Intangible means I can't touch it. I can't see it. It doesn't exist in the physical sense. So think about motivation. If I asked 5 students from this class, how motivated are you for this class? Someone might have the motivation of needing to make an A, and somebody else might have the motivation to just pass the class. Those are two different sets of responses, right? Motivation it's a spectrum there. But if I don't clearly define what motivation is, our research conversation between me and another researcher, it goes out the window. Same thing is true with something like self-esteem or sleep quality. I could have two people sleep 8 hours. One of them sleep very restlessly, tossing and turning, getting up multiple times during the night, but they slept 8 hours. And then I could have someone else who slept like a log, like a baby for 8 hours, didn't wake up, didn't turn over. Those two people could say, my sleep was great, but they're very abstract in the way that it happened. So measuring variables that are intangible or constructs that are intangible is a complicated topic. Theories are sets of statements about mechanisms underlying a certain behavior. Okay, so a theory is a combination of statements that are all put together that explains something. So I'm going to pull an example in from something that has absolutely nothing to do with psychology, and I'm going to talk about the theory of plate tectonics for a moment. So plate tectonics is, there's a theory of plate tectonics that states that there are mechanisms underneath the Earth's surface in the mantle, convection currents that rise and fall, and as those currents rise and fall in the asthenosphere, which is the layer between the mantle and the crust, that kind of an overlap there, those plates move, and they're propelled along by those convection currents.
Could you try again?
I apologize, because apparently Siri has decided to start talking to me, and I don't know why. I apologize about that. Anyway, but that theory of plate tectonics came about from observing behavior over a long period of time, and theories can often not be actually proven. So in the case of plate tectonics, I can't go back in time or even in a period of time and watch these plates move. But I have a bunch of different observations and a bunch of other evidence that help me come up with a theory to explain the behavior of how continents move. Now, we have the same thing in psychology as well. But constructs or hypothetical constructs are things that come out of theory and speculation. We can't see them, but we can assume that they exist. And because they have a clear definition that has come from a lot of different research from many, many researchers over long periods of time, we can use them to help explain and predict behavior, whether it be human behavior or cat behavior. So, how do researchers talk about variables and their research? Well, they do so by applying the concept of operationalizing them. I have a hard time saying the word operationalize, so if I stumble over it, I apologize. But when we operationalize a variable, we take methods and define those constructs in measurable terms. We create a definition that is an operational definition. That means I set specific criteria about that behavior or whatever it is that I'm trying to measure. And because I have those specific criteria in place, I explain those criteria to another researcher. And that way, when we're talking about whatever it is we're talking about, we're on the same page and we're not misinterpreting whatever it is that we're attempting to study. So an example, intelligence, we can operationalize that as an IQ. You could give someone a standardized IQ test, and that way I'm on the same page when I talk about someone saying they have an IQ of about 100. There is a set of specific expectations when it comes to IQ that I can have for someone who has an IQ of 100. Or maybe someone has an IQ below 80. I have a set of expectations based on the behavior and the definition that I have given to IQ. Another example, In this video is hunger. Hunger can be defined as total hours of food deprivation. Deprivation meaning that I'm not eating, not giving it to someone. That's a operational definition, but it doesn't often completely explain maybe the feeling that you have inside. Maybe I could be deprived of food for 8 hours and not be as, quote, hungry as someone who has a different definition of hunger. But for the intent and purpose of that research, we could say hunger is total number of hours deprived of food. Now, operational definitions and constructs are different. Construct is that overarching theory, the conceptual thing that is out there that we're studying, okay? There are concerns as a researcher that we have about operational definition and their creation and how that goes along with the quality of our measurements. So the definition and the construct may not always correspond exactly. So the example here in the video says, for example, test performance may not reflect knowledge. If I give you a test on how to put together a combustion engine, I definitely would fail that. Bottoms, just no problem. I know nothing about combustion engines except they combust stuff and they make things go. But I could also have a person who works with engines come in and tear apart that engine and then put it back together. And that's two different ways of measuring knowledge about combustion engines. So their performance on that task may not be as reflective as the answers on a test. So there's often a difference between how we measure something and the actuality. An operational definition also can leave out important parts of a construct. So let's go back and talk about sleep quality. Earlier I said I could ask 2 different people who slept 8 hours, how they slept, and they could give me an answer. Well, I can look at 5 or 6 different things off the top of my head that I could say would have something to do with sleep quality. How long did I sleep? How many times did I wake up? How many times did I turn over? I can bring in the physiological components of it. How long was I in deep sleep? How long was I in REM? Whatever. If I omit something from that, I might not have a clear picture of what sleep quality is. My operational definition is missing something. And then sometimes we may include things in our operational definition that really don't have anything to do with that particular concept that I'm talking about. So you can have too much, too little. It just depends. But the bottom line is it's really important as a researcher to have a good operational definition. So how do researchers come up with a good operational definition? A lot of times they look back to previous research. Previous researchers have often defined their operational definitions in ways that have obviously panned out. But you may have some reason to add some new part to it to build upon the conventional way that someone measured something in a previous study. So let's talk about variables. Now that you know what the operational definition is of something and how a construct is this huge theoretical intangible thing, as a researcher, you've got to come and narrow it down into variables, because variables are the heart of what we're getting at when we're conducting research. So there are many, many types of variables. The first one that we're going to talk about is the independent variable. So the independent variable is the variable that you, the researcher, are manipulating or controlling or selecting, depending on the situation, because you want to find out if that independent variable causes a change in another variable. Now remember, this is an experimental class. This video is geared towards experimental. And in an experimental study, I'm looking to determine cause and effect. So whereas in a non-experimental class, I'm looking to see if there's an association. Now I'm looking to see if there's a direct change, if one is causing the other. So in an experiment, the independent variable is what we are assuming causes the effect. So let's talk about it within the concept of something that you can imagine. Say you're a researcher and you want to know about how caffeine affects people when they take tests. So I give a class a caffeine supplement, and I give another class a placebo, a pill that has no caffeine in it, a sugar pill. And then I give them a test, and I measure their performance on it. The thing that I am studying to determine if there is an effect is caffeine. So in this particular situation, the independent variable would be caffeine. Okay. Sometimes we also call it the experimental variable. And there is an acronym that I use to teach my students in high school how to remember things. So the word mix, M stands for manipulated, I stands for independent, and the X is for x-axis. I'm sorry, I cannot draw with a mouse very well. So that means if I have a graph here, this is my x-axis here. This is where I'm going to graph my independent variable on the x-axis. So I would have caffeine versus no caffeine, and then test performance over here. So the independent variable is linked to the dependent variable. Dependent variable is the outcome that you're measuring, okay? That's how you can remember it there, measure. So if you had mix, manipulated, independent, x-axis, you can remember the word dry for the dependent variable. So the D from dry is dependent because it's expected to depend on my independent variable. R stands for response because it's often called the response variable. You're giving a dose, you're expecting a response. And then we also graph the sorry, I lost my mouse here. I'm trying to find it. There we go. We graph the response or the dependent variable on this axis over here. So that's my y-axis. So my test performance would be here, caffeine, no caffeine. Maybe my caffeine people did this and my no caffeine people did that. So mix, dry. We also have another set of variables that are very, very important, especially in experiments, and those are control variables. And a control variable is any variable that you want to keep constant across experimental conditions, because I don't want that control variable to influence any of my results. Because a control variable can also be seen as an alternative explanation. So in the particular study we were talking about earlier, the situation with the caffeine and the test, I want to make sure that I'm giving my test in the same room, okay? I want to have the same test that I'm giving them. I don't want to give one group a very hard test and the other group a really easy test. I also want to keep the time under the same amount for both groups, right? So those are just a couple of examples, but in a real research situation, there would be a lot of different variables that we would want to control, because we want to make sure that if I'm making the claim that variable X causes variable Y, I need to make sure that all of my other variables have been accounted for. Otherwise, that claim that I'm making may not actually be true, and that's not something we want. All right, so we also have to worry about extraneous variables. And extraneous variables are variables other than the independent variable, that could be affecting the dependent variable. They're not the focus of the study, but they could influence the outcome. So, and you can't necessarily control for these things. So think about the example of the caffeine and the test. My controls were the same kind of test, the same time, the same room, but those things can be controlled. But I can't control how much knowledge a person has before they walk in and take that test. I can't control how long they've slept. I can't control whether or not they have test anxiety. and I can't control whether or not they're even motivated to be there. Excuse me. So those are all things that are extraneous. We also have confounding variables. These are a particular kind of extraneous variables that vary systematically or along with the independent variable. So it makes it really hard to determine whether or not any cause that was seen is actually due to my independent variable or if it's because of something else. So the example here says if students in the caffeine group take the test in the morning and students in the no caffeine group take it in the afternoon, I have a confounding variable with time of day, because time of day, I mean, we may be more motivated to take the test in the morning and we may just simply do better. So there's ways to control for confounding variables such as that, and we will talk about that when we get more into experimental design as we progress in the course. So for now, just keep in mind that confounding variables are out there. You might also hear the term measured variable. Measured variable is the variable that is being observed and recorded, but it's not manipulated. And in an experiment, this is going to be your dependent variable. It's the thing that you're measuring. Could be GPA, could be age, anxiety level. All of those things could be considered measured variables. So in the example here, it says a researcher may manipulate study method, but measure test scores, motivation, and anxiety. So they're measuring those things, but they're not manipulating them. And again, a manipulated variable is your independent variable. That is the active variable that you are setting the levels for in your experiment, and it may have different levels in that experimental condition. So I could be doing my caffeine study. I could give one group 1 dose of caffeine. I might give another group a double dose of caffeine. So I'm manipulating caffeine level. All right. Your outcome variable is the variable that we use to assess the effect of the independent variable. It's another word for your dependent variable. So maybe I'm looking at reaction time or test score, how many errors you make, how stressed you are. All of those things could be considered outcome variables. Predictor variables are variables that we use to predict a change in another variable. In experiments, we can consider the independent variable to be our predictor. But you're going to hear predictor more often in correlation and regression research, which is considered non-experimental. So an example here says treatment condition may be used as a predictor for depression scores. So maybe somebody who is in therapy might have a higher depression score than someone who is not if they've been exposed to an event that would be associated with depression. We might use a criterion variable too. Criterion variable is the variable that's being predicted. So in experiments, it's usually the dependent variable, but it is, again, often heard in regression and prediction-focused research. Then moderators are something that we will talk about later on in the course when we get into ANOVA and some more of our statistics, but a moderator is a variable that is going to affect the strength or direction of a relationship. So there's a relationship that exists out there, but a moderator comes along and it pushes that relationship stronger, or it may decrease it just depending on what you're talking about. So there's an example here that says a tutoring program may improve grades more strongly for students with low prior knowledge than students with higher prior knowledge. So prior knowledge is a moderator. I have a test that I want to give to my students, okay? A student that hasn't seen this material before versus a student that has seen the material, okay? I have a tutoring program. That tutoring program is going to help those, it's what I'm testing, right? I want to measure grade improvement. But prior knowledge is going to be a moderator. Mediators are variables that explain how or why that independent variable is affected by to the dependent variable. So it gives us the process by which that effect is occurring. So the example in this particular slide is about exercise, and it says if exercises reduce depression symptoms, it might actually be helping you sleep better. And by helping you sleep better, you feel better when it comes to depression. So it kind of like works through something, which is the definition of what a mediator is. A mediator is someone who helps, two groups work through something, like a divorce, okay? Those are just some of the many variables that you're going to have out there in our research world. And the last one I believe in my slides here is a nuisance variable. A nuisance variable is it's something that exists out there that is not of theoretical interest, but it may be adding some sort of noise or unwanted variability to the data that you're looking at. So what you as the researcher are going to try to do is you're going to try to minimize or control for those nuisance variables. And an example of this would be in our caffeine experiment. Let's talk about noise and room temperature. So if I'm doing my caffeine experiment, I have my two different groups of students, they're taking their test, and all of a sudden the air conditioner breaks and it's 90 degrees in Texas on the day that they're taking their test. That temperature has now become a nuisance variable. Somebody running a lawnmower outside of a classroom window, that is also a nuisance variable. So it wasn't of theoretical interest. We didn't anticipate that, but it happened, and it very well could have influenced the results of the test that we're giving, and therefore had some impact on our research. So now that you know all about variables, let's review some validity and reliability and talk about how we measure variables. So there are two essential criteria that researchers have to always keep in mind when we're talking about the design of high quality research, and those are validity and reliability. Both of these constructs are typically defined and evaluated by the consistency of the relationship between the measurement set that you have. So when we talk about validity and reliability, we are always talking about measurement at the same time. And how does this relate back to variables? Well, measuring variables is what we do when it comes to research. So we have to make sure that the way that we're measuring those variables and the tools that we're using are both valid and reliable. We want to be able to demonstrate consistency in a relationship. If an experiment exists in order to prove a causal relationship between two variables, X and Y, then I need to have a measurement that is going to consistently demonstrate that relationship. So what I do is I demonstrate that consistency by taking measurements and comparing them to other measurements that were taken at different points in time. So say I have two scores, one from a new and one from a well-established measure. So let's take it, I come up with a sleep quality tool. I come up with a brand new way of measuring sleep quality, right? And I want to prove that my tool is valid and reliable when it comes to measuring sleep quality. Pretend for a moment that we've established our operational definition. All of that stuff has been done when it comes to sleep quality, right? We're on the right page. We're now moving to the point where we want to make sure that this measurement does what it says that it's going to do. So what I might do is take a well-established measurement tool like the Pittsburgh Sleep Quality Index, the PSYC, and I give that to a group of people. And to that same group, I also give my new sleep measurement. And what I want to see is consistency of a relationship. Now, when I have a positive relationship, that means my measurements change together in the same direction. And when I have a negative relationship, that means that they are varying in opposite directions. And if you've taken 4370 non-experimental research, especially if you've taken it with me, you should be quite familiar with this. This would be Pearson's correlation. You're looking at, as one variable changes, does the other change as well? So what we do is we demonstrate that relationship by calculating Pearson's R, which, remember, exists from a negative to a positive. It's 1, a perfect correlation, remember, would be a positive. Perfect positive would be a 1, positive 1. So on the screen here, you've got 3 different levels. You've got the consistent positive. That's going to give you your Pearson's R at about 1. A negative would be a -1, and then an inconsistent relationship would be something close to 0. That means there's no correlation going on. So here is an example of how we can conceptualize it in an image. So if I have a positive correlation with my first measure and my second measure, I've got a nice line showing everything's going up. Negative, it's going this way. I have clear, I can draw a clear line of fit between the two. Down here, I don't have anything going on except for a glob of dots. That's showing me that there is no relationship going on in that situation. Now, to achieve validity, your measurement procedure has to accurately capture your variable that it's designed to measure. Okay, we talked about intelligence as being a hypothetical construct. It's something that's intangible. I can't observe it. Therefore, it's very difficult to measure it. So how do I really know if an IQ test measures intelligence accurately? Okay, we have to go through procedures to establish the validity of tests, including IQ tests, so that we can be assured that they're measuring what they say they're going to measure. There's a lot of different kinds of validity. We've talked about these in previous classes. Face validity is the most straightforward and the least scientific form. Face validity basically says, does it look like it measures what it says it measures? That's why on the video here, you'll see it says superficially appear. Superficial and appear are both very subjective terms. So, in other words, does this look like it's going to measure what it says it's going to measure? So face validity, yes, it's important, but it's probably one of the least scientific forms of validity that's out there. We have an example underneath here that says, does a test of optimism appear to measure a positive attitude? I mean, obviously, if it measures something about polka dots, then no, it's not. Concurrent validity is the agreement between scores obtained using 2 or more measures. This is getting at a bit more scientific in nature. So think about the PSYC that I was telling you about earlier and Dr. Gonzalez's new and improved sleep quality measure. So do the scores from the PSYC and the scores from Dr. Gonzalez's new measure, do they both agree when it comes to the aspects of sleep quality? The example here on the video talks about, does the results of a journalism program entrance exam correlate with the SAT verbal section? So if they had concurrent validity, then yes, those two, the section on the verbal section and the entrance exam scores would have a high level of correlation. Now, predictive validity means that do the scores that we obtain from a measure accurately predict behavior according to a theory? So if I have a theory about something, so say we talk about engineering being a heavily mathematical major, so I would predict that someone who scored very high on the SAT Math 2 subject exam to do well in at least the math portion of an undergraduate engineering program. Construct validity talks about how the scores obtained from that measurement behave like the variable. So does the person who scores highly on an optimist test usually exhibit an upbeat attitude? A measure would not have very good construct validity if a person didn't engage in optimistic behaviors. However, if they scored high on the optimist test. Convergent validity is when we have a strong relationship that's demonstrated between two scores or two methods that are measuring the same construct. So we have the SAT and we have, I'm going to go with the ACT instead of what's on the video here, the GRE. But the SAT is a college entrance exam. And where I'm from, the ACT is the standard college entrance exam. Both of them have a math section on them. So I would expect someone who scored high on the math subject portion of the SAT to also score high on the math portion of the ACT. Then divergent validity is when you have little to no relationship between measurements of different constructs. So I like the example here. It says, do SAT math subject exam scores show no or limited correlation with scores on the Beck Depression Inventory? So the Beck Depression Inventory is a measurement tool for measuring depression. And if I gave that tool to someone, I shouldn't expect to see any sort of relationship or positive correlation between the BDI score and the math subscore on the SAT. Because those are two totally different things. And that's where diverge means to move in two different directions. So that makes logical sense. This is a nice little image that I found that talks about how we can take an example of a variable and we can test validity with it. So hunger is our variable. And there are several different things that we can confidently assume would affect your hunger. Number one, food deprivation. How long has it been since you've eaten? I can also look at your blood sugar. If your sugar is low, I can assume that you have not eaten in a while. And then maybe time of day. If you have not eaten since noon and it's getting close to supper or dinner time, then I might assume that you are hungry. So those variables are going to give construct validity to my 8 scale. 8 scale is the fictional hunger scale that we're talking about in this. And I'm going to have concurrent validity and convergent validity. Concurrent validity would be initiating a meal. I eat because I'm hungry. So that backs up the idea that my 8 scale is saying you're hungry. Eating is a behavior that you do when you're hungry. That's concurrent validity. I can look at predictive validity. If I start seeing you looking at food, opening the pantry door, looking in the refrigerator, those are things that also show that there's hunger going on. Divergent validity is thirst, okay? I'm talking about food here, not necessarily talking about drink. And then another example in it would be the convergent validity, spending money on food. So if you're hungry, you're eating, you may have to purchase that food, therefore convergently spending would increase as well. Now that we've talked about validity, let's talk about reliability. So when you think about a person who is reliable, you can think of them as someone who can be counted on, right? Your best friend, a reliable person. You can consistently think that they're going to be there for you when you need to talk. So reliability refers to the stability of the measurement. Is it going to give me what I need every single time? And measurement inconsistency is going to be related to different kinds of error. Okay, there's a lot of different kinds of error that can exist out there. We'll talk about a couple of them. But anytime something becomes not reliable, there's some sort of error that is going on. So a reliability calculation can be boiled down to the measured score is the true score plus the error that is out there. The greater the error, the greater the inconsistency between reality and what you've recorded. Therefore, your measure has lower reliability. So there's lots of different sources. I'm going to escape out of this for just a moment and I'm going to fix this, because that's going to bother me when I print your notes out. So let's fix that now. And we'll flip that back around. All right, so reliability of measurement, sources of measurement error. First of all, it can be the observer. So if I'm observing human behavior and not using a tool, say I have an observer in a room who is counting the number of times that a student engages in disruptive behaviors. That human making those measurements can accidentally, for whatever reason, not count or overcount the number of times a student interrupts the teacher. That might be based on their attention just kind of, going out the window. Maybe they're tired. Maybe they got distracted by something else, whatever. So observer error obviously has to do with the observer not being reliable. We can also have environmental changes. It's sometimes challenging to have the same identical circumstances in every situation during an experiment. Earlier we talked about tests and giving a test while somebody was mowing the yard outside, or if the AC breaks. Those are both examples of environmental changes that were extraneous variables, but they definitely can affect the reliability of your measurement. At the same time, you can also have issues with your participants. Your participant might be tired. Maybe they didn't get a good night's sleep. That can change between your different measurements. We also have this concept with our successive measurements. So we want something called test-retest reliability to be high. Test-retest reliability means that I compare the scores between 2 sessions of measurements for the same individuals or conditions, and those scores are highly correlated. So I give my test to a person on Monday, and I give the same test to them again on Friday. I want those measurements to be very close, unless the goal of my experiment was to induce some sort of change. We often use parallel forms of reliability, and that uses 2 different versions of the same test. So maybe I give test A on Monday and test B on Friday. They're measuring the same thing, but the questions may be in different order. The answers may be listed in a different way, but it's essentially the same test. Or I can do it through simultaneous measurements. We run into this when we have inter-rater reliability. So thinking back to the situation where I have an observer in a classroom looking at the number of times that a student interrupts the teacher, if I add a second observer to that and I compare their measurements, observer 1 says there were 5 interruptions, observer 2 says there were 8, there's definitely something going on because their reliability, the inter-rater reliability between the 2 observers is off. We want their agreement to be high because they're observing and counting those behaviors. We also have internal consistency when it comes to our measures. So we can test that internal consistency by looking at split half reliability. And that's a procedure where we split a test in half. We can have first or second, odd versus even, or we can have randomly, and we can compute a score for each half. And we want to compare the consistency between those 2 scores of participants. Now, reliability and validity are dependent on one another. I have to have reliability in order to have validity. Okay? I cannot have a measure that claims to be valid if it's not reliable. So in other words, if I develop my wonderful new sleep quality scale, Dr. Gonzalez's sleep quality test, right? And I give it to my participants, and I claim that it's valid, I can't turn around and give it again, and then it come up with a totally different set of results that completely shows it's not reliable. So reliability has to exist in order for validity to be true. Now, a measurement can still be valid, but not reliable. So you have to remember that just because something is consistent, it doesn't mean that it is valid. It's consistently giving you results, but those results could be way off the bullseye of what you're aiming to measure. Let's talk about scales of measurement for a minute. So remember, measurement is a procedure that we use in order to gather data, classify individuals in observation, and we use different scales in order to talk about the different categories that we can put those measurements in. And there's 2 components to that. We can have the set of categories and the assignment procedure. So nominal scale, nominal is another word for name. Name refers to a qualitative difference. Qualitative means a word, a category, color, red, green, and blue are all examples of color categories. So red, green, and blue would be nominal. Male and female, nominal. Ordinal represents a difference in a series of ranks, like the scale that you see on the screen below there. It says strongly disagree, somewhat disagree, neutral, somewhat agree, and strongly agree. So I've got categories, right? And they're put in order. There's no zero, though, but there is a difference between each one of these. Now, you got to be careful with ordinal because a lot of times they'll talk about a race. You have 10 runners and they're running the 100-meter dash, right? And you have one person who comes in first, and you can assume that they were the fastest, right? Well, then you have a second runner who comes in second, and then a third runner that comes in third. The distance between 1 and 2 is not necessarily the same as the difference between runner 2 and 3. So while this is an ordinal scale here, it doesn't go into that lack of consistency between different measures. In fact, this one actually shows me a consistent. There's, if I divided the distance between 1 and 2 into 10 pieces, then I would have 10 different degrees of difference between strongly disagree and somewhat disagree. So just be careful with that. Interval and ratio scales are going to be very useful when you get into your statistics in the second half of this course. Interval scales have equal intervals between one and another. So think of like a ruler, and you've got inch number 2 and inch number 7, and the distance between inch 2 and 3 and the distance between inch 7 and 8 are going to be the same. Now, if I add a true zero to that, I now have a ratio scale. So think about temperature. Temperature, Celsius and Fahrenheit, are considered interval scales because there is no 0 degree, right? Think about temperature as in like your body when you have a fever. Obviously, if you had a 0 degree fever, you wouldn't be alive, and that would be a problem. Now, this particular book that I got, this particular presentation from, throws in 0 Kelvin signifies heat death, no heat or molecular motion. So just remember that if I take an interval scale and I add an absolute 0 to it, a true 0 to it, I now have a ratio scale. Now, interval and ratio scale scores are really good for doing math. So we can use them for statistical analysis, and they allow us to do hypothesis testing. Now, when I have an ordinal scale, it's not usually compatible with basic math or statistics, and what I have to do is code it. So it can be challenging to use ordinal or even nominal if you don't do some sort of coding. So what's the scale's ability to compare different measurements? A nominal scale can tell me if there is a difference that exists, and that's it. Is it male? Is it female? Is it red? Is it blue? That's all it can tell me. Ordinal can then tell me a direction. Is it larger? Is it smaller? Is it shorter? Is it taller? Interval can then tell me the direction and the magnitude because there's a difference between each one of those intervals. And then if I add a 0 to that, now I can calculate a ratio. So what you can see here is that as you go from nominal to ordinal, interval, and ratio, the complexity of the measurement gets a little bit more. It increases a little bit. I like this this table. I included it in here for you to look at, and it's in the notes, and it basically summarizes what we just talked about by listing out your scales of measurement, by telling me what kind of information each scale does, and then by giving an example. And this time it did use the race. So I have nominal as category. It's the kind of athlete. Is it a marathon runner versus a sprinter? Ordinal, did they come in first, second, or third? Interval, the time that it took for them to finish the race. And then ratio adds the 0 component to it. All right, let's continue and talk about modalities of measurement. So modalities of measurement refers to the way that we collect our data. First, we have self-report measures, and self-report is very self-explanatory. This is when we ask our participants to directly answer a question about their behavior. So it gives us a good measure. It's coming straight from the source, but the problem is it can be dubious when it comes to validity, because we as humans inherently remember things the way we remember them. I might tell you that I slept well last night, but the reality is I may have woken up several times, and I might be downplaying that for whatever reason. There are many different reasons why self-reporting measures and the people giving that data may downplay or enhance whatever it is that they're trying to report. Physiological measures are a little bit different. These are when we record some manifestation of the construct. So they give galvanic skin response and MRIs as examples. They're very objective. Sometimes they use really expensive equipment. So if I'm going to do a functional MRI, I need to have this MRI machine. And they're collecting data on a very specific physiological thing. So you might lose some of the nuances behind whatever it is that you are trying to measure. Now, behavioral measures are based on activities that we can observe and we can record. So this gives the researcher a bit more flexibility. So a behavior that is good to define and measure for that construct might be used. So when we talk about sleep quality, we might talk about how long you slept, how many times you woke up, and then maybe how many times you rolled over. So those are three things that I can put together. Those are three behaviors that I can measure, and then I can come up with a score. But you have to always keep in mind that a behavior can be temporary or it might be situational, and it might not be the best indicator for that underlying construct that we're trying to get at. Let's talk about a couple of other aspects of measurement. We need to always keep in mind multiple measures are important, because the more times I collect a measure, that gives me a lot more confidence in the validity. But at the same time, it also introduces problems. So if I measure a behavior multiple times, it might mean I need to use a more complicated statistical analysis in order to interpret whatever it is I'm trying to interpret. Anytime I start measuring something at more than one point, there's always the possibility that there's a lack of agreement between those two measures. That is your reliability, right? Now, we can control those things to a certain extent, but one of the things that a researcher might do is then combine those different points of measurement together to get a single score. So the PSYC is a good example of that. The PSYC, the Pittsburgh Sleep Quality Index, it's a scale about sleep quality, and it has about 10 or 11 different questions that look at several different aspects of sleep. So by combining them into one score, I'm not giving any one particular aspect of that construct more weight than the others. We also have to keep in mind that there is always going to be a concern with sensitivity and the range. So the range effect is when a measurement procedure is insufficiently sensitive to detect a difference. We have two concepts here, the ceiling effect and the floor effect. The ceiling effect happens when the scores cluster at the high end of the scale, and there's no possibility for it to go past that. So you've hit the ceiling, in other words. And the floor effect is the opposite of that. Your scores cluster at the low end, and there's no possibility for a decrease in value. We also have to keep in mind that artifacts exist. Artifacts are artificial features that are accidentally introduced into our procedure. One of these is an experimenter bias, and that's when you, the experimenter, your expectation actually influences the outcome of the study. Think back to the observer in the classroom looking at the number of times that a student interrupts the teacher or causes a disturbance. There could be just an inherent need for the teacher or the observer to overmark things that are not necessarily inherently an interruption. Therefore, the number of interruptions is inflated. how do we limit experimenter bias? We can do that by doing our study in a certain way that helps to standardize or automate our procedures. Single blind studies is when we have a study conducted by what's called a naive experimenter. So that means one person is unaware of the expected results. And a double blind study is when both the experimenter and the participants are naive. We also have to keep in mind that there are demand characteristics that can happen at any point in time during a research situation. These are going to be cues or other signals that might suggest to the participants how they need to behave, or what the purpose of the study is, or what our hypothesis is. And by having those cues or characteristics there, we are inadvertently influencing our participants to behave a certain way. And that goes along with reactivity. Reactivity is when our participants then modify their behavior to respond to the demand that you're putting on them. So just because that observer is in the room, maybe the students interrupt the teacher less than they normally would if there wasn't an observer. So you run into different classifications of participants. You can have a good subject role. That's the person who supports the experimenter's hypothesis. You might also have a negativistic subject. That's one who's going to act contrary to your hypothesis. There's always the possibility of an apprehensive subject. That's the one who presents themselves in a good light, but, they're apprehensive. And then your faithful subject role is someone who follows the instructions strictly to the letter of the law. And that is the ideal participant that we want to have. Now, how do you know how to select your measurement procedure? Go back to the literature first. If there are different procedures that exist, you need to evaluate the different ones that are out there, look at the expectations of your study, and then come up with the one that's going to best answer your research question. So at the end of this video now, you should understand constructs and how they're important to psychology. We should know about operationalizing variables. You should know about all the different types of variables that we talked about. You should be able to tell me about positive and negative relationships, validity and reliability, your 4 measurement scales, and some threats to validity and reliability, and especially those that are related to artifacts. All right, let's continue and talk about modalities of measurement. So modalities of measurement refers to the way that we collect our data. First, we have self-report measures, and self-report is very self-explanatory. This is when we ask our participants to directly answer a question about their behavior. So it gives us a good measure. It's coming straight from the source, but the problem is it can be dubious when it comes to validity, because we as humans inherently remember things the way we remember them. I might tell you that I slept well last night, but the reality is I may have woken up several times, and I might be downplaying that for whatever reason. There are many different reasons why self-reporting measures and the people giving that data may downplay or enhance whatever it is that they're trying to report. Physiological measures are a little bit different. These are when we record some manifestation of the construct. So they give galvanic skin response and MRIs as examples. They're very objective. Sometimes they use really expensive equipment. So if I'm going to do a functional MRI, I need to have this MRI machine. And they're collecting data on a very specific physiological thing. So you might lose some of the nuances behind whatever it is that you are trying to measure. Now, behavioral measures are based on activities that we can observe and we can record. So this gives the researcher a bit more flexibility. So a behavior that is good to define and measure for that construct might be used. So when we talk about sleep quality, we might talk about how long you slept, how many times you woke up, and then maybe how many times you rolled over. So those are 3 things that I can put together. Those are 3 behaviors that I can measure, and then I can come up with a score. But you have to always keep in mind that a behavior can be temporary or it might be situational, and it might not be the best indicator for that underlying construct that we're trying to get at. Let's talk about a couple of other aspects of measurement. We need to always keep in mind multiple measures are important, because the more times I collect a measure, that gives me a lot more confidence in the validity. But at the same time, it also introduces problems. So if I measure a behavior multiple times, it might mean I need to use a more complicated statistical analysis in order to interpret whatever it is I'm trying to interpret. Anytime I start measuring something at more than one point, there's always the possibility that there's a lack of agreement between those 2 measures. That is your reliability, right? Now, we can control those things to a certain extent, but one of the things that a researcher might do is then combine those different points of measurement together to get a single score. So the PSYC is a good example of that. The PSYC, the Pittsburgh Sleep Quality Index, it's a scale about sleep quality, and it has about 10 or 11 different questions that look at several different aspects of sleep. So by combining them into one score, I'm not giving any one particular aspect of that construct more weight than the others. We also have to keep in mind that there is always going to be a concern with sensitivity and the range. So the range effect is when a measurement procedure is insufficiently sensitive to detect a difference. We have 2 concepts here, the ceiling effect and the floor effect. The ceiling effect happens when the scores cluster at the high end of the scale, and there's no possibility for it to go past that. So you've hit the ceiling, in other words. And the floor effect is the opposite of that. Your scores cluster at the low end, and there's no possibility for a decrease in value. We also have to keep in mind that artifacts exist. Artifacts are artificial features that are accidentally introduced into our procedure. One of these is an experimenter bias, and that's when you, the experimenter, your expectation actually influences the outcome of the study. Think back to the observer in the classroom looking at the number of times that a student interrupts the teacher or causes a disturbance. There could be just an inherent need for the teacher or the observer to overmark things that are not necessarily inherently an interruption. Therefore, the number of interruptions is inflated. How do we limit experimenter bias? We can do that by doing our study in a certain way that helps to standardize or automate our procedures. Single-blind studies is when we have a study conducted by what's called a naive experimenter. So that means one person is unaware of the expected results. And a double-blind study is when both the experimenter and the participants are naive. We also have to keep in mind that there are demand characteristics that can happen at any point in time during a research situation. These are going to be cues or other signals that might suggest to the participants how they need to behave, or what the purpose of the study is, or what our hypothesis is. And by having those cues or characteristics there, we are inadvertently influencing our participants to behave a certain way. And that goes along with reactivity. Reactivity is when our participants then modify their behavior to respond to the demand that you're putting on them. So just because that observer is in the room, maybe the students interrupt the teacher less than they normally would if there wasn't an observer. So you run into different classifications of participants. You can have a good subject role that's the person who supports the experimenter's hypothesis. You might also have a negativistic subject, that's one who's going to act contrary to your hypothesis. There's always the possibility of an apprehensive subject. That's the one who presents themselves in a good light, but, they're apprehensive. And then your faithful subject role is someone who follows the instructions strictly to the letter of the law. And that is the ideal participant that we want to have. Now, how do you know how to select your measurement procedure? Go back to the literature first. If there are different procedures that exist, you need to evaluate the different ones that are out there, look at the expectations of your study, and then come up with the one that's going to best answer your research question. So at the end of this video now, you should understand constructs and how they're important to psychology. We should know about operationalizing variables. You should know about all the different types of variables that we talked about. You should be able to tell me about positive and negative relationships, validity and reliability, your 4 measurement scales, and some threats to validity and reliability, and especially those that are related to artifacts.